Another type of problem that you see in this particular area of the criteria for precipitation is something called selective precipitation. And in the selective precipitation example, what we're going to do is we're going to try to separate certain ions based on their solubility. So typically we'll set something like this up, where we're going to say that when we set up this example, we have silver nitrate, which is AgNO3. We'll take a solution, is added dropwise to a solution made to be 0.005 molar in carbonate ion, which is CO3 2-, and 0.005 molar arsenate, which is AsO4 3-. Which species will precipitate first? And the second part of this question will say, what concentration of silver plus will give the best separation? And what we're going to do here is we're going to take a beaker right here, which we have a solution, and in this solution we're going to have AsO4 3- ions, and we're going to have CO3 2- ions. What we can do is we can set up a burette down here, and we're going to dropwise, we're going to add Ag plus and NO3-. The NO3- is always going to be a spectator ion. But as we're adding this dropwise, we're going to put silver plus in this solution. So we could potentially form a precipitate between Ag3ASO4, and we can also form a precipitate between Ag2CO3. A lot of times, if you have a contaminant in water, we want to add one species to remove one particular ion, but maybe you want to keep that other ion in solution. Okay? So in your drinking water, for example, you want to have fluoride ions in there because they can prevent tooth decay or prevent cavities. But you don't want to drink, say, mercury or lead or anything like that. So the question is, how can we selectively remove these things? So in this particular case, we're going to talk about how could we maybe selectively separate these guys. So what we could have happen here in this beaker are one of two things. We could form Ag2CO3 solid and have that in equilibrium with our silver ions in solution plus CO3 2- ions in solution. We have a 2-to-1 ratio of cation to anion, so we need a 2 in front of the silver right here. And the KSP for this particular equilibrium is 8.1 times 10 to the minus 12. At the same time, we also have Ag3ASO4 that could form as a solid, which will be in equilibrium with 3 Ag plus in aqueous solution, plus ASO4 3-, also in aqueous solution. The KSP for this is equal to 1.0 times 10 to the minus 22. We need to now look at our Q expression. Our Q is going to equal the concentration of Ag plus, that quantity squared, times the concentration of CO3 2-. And over here for our second expression, we're going to have the silver concentration to the third power times the ASO4 3- concentration. We know that right at the point where we can saturate our solution and come to equilibrium, that the Q is going to be equal to the K. So what's going to happen here is, as we're dropping in this solution of silver plus, there's going to be a certain point where this threshold is reached where a first precipitate is going to form. So when we're adding this, if we set Q equal to K, we can solve for the concentration of silver that it's going to take to initiate a precipitation. And each of these examples is going to be slightly different because in one case, you have a silver concentration squared, and in another case, you have a silver concentration to the third power. So what we can do here for the case of the silver carbonate is if we rearrange the Q expression right here, we can say that the concentration of the silver plus that we need to form a precipitate is going to be equal to the Q, which is, or the KSP, which is 8.1 times 10 to the minus 12, divided by our carbonate concentration, which is going to be 0.005, and we're going to have to take the square root of all of this because the silver concentration is raised to the second power. Over here for the silver arsenate case, we have Ag plus concentration is going to equal the KSP, which is 1.0 times 10 to the minus 22, divided by 0.005. And we're going to have to take this all to the 1/3 power because our silver plus concentration is raised to that 1/3 power. So if we go through now and calculate for our silver plus concentration, for the case of the silver carbonate, we're going to get 4.0 times 10 to the minus 5 molar. And when we calculate a value, especially when we're looking at the solubility problems, we have a silver concentration equal to 4.0 times 10 to the minus 5. We want to say exactly what this concentration is. Okay? This concentration right here is the concentration of Ag plus needed to initiate a precipitate of Ag2CO3 when 0.005 molar CO3 2 minus ions are present. So this is how much silver we need in order to start the precipitation. Likewise, we can do the same thing and calculate another concentration for silver, which happens to be 2.7 times 10 to the minus 7 molar. And the second calculated value is the concentration of silver plus ions needed to initiate a precipitation of Ag3ASO4 when 0.005 molar ASO4 3 minus ions are present. So this leads us to be able to answer the two questions that were asked. The first question that asked is which ion or which solid will precipitate first, and the second one was when will or what would the best separation be? And the way I like to set these up is I like to set this up kind of as a little scale right here. We're going to say that this is our silver plus ion concentration that's present. Initially, this value right here is going to be 0. And if we have 0 silver ions present, what we can look at would be the ions that we would have in solution. And those ions that we would have in solution would be the CO3 2 minus and the ASO4 3 minus. So at a concentration of 0 for silver, these are the ions that we have. We start drop-wise adding the silver. We're adding 1 drop of silver ions to 250 milliliters. So the concentration is not going to change that much. But as we keep dropping and dropping and dropping, we can observe a precipitate to form. In terms of which one will precipitate first, it's going to be the smallest concentration of silver that's needed. Because as we add every drop of that silver plus ion in solution, a precipitate, or the concentration of the silver is going to get higher and higher, and the likelihood of the precipitate happening is much greater. So at a concentration, we'll say right here, which would be 4.0 times 10 to the minus 5 molar, that's when we're going to observe our first precipitate. So before we get to that value, though, we're going to have our CO3 2 minus ions in solution, plus our ASO4 3 minus ions in solution. And in addition to those 2 ions, we're going to have a very, very small amount of silver plus ions in solution, plus our nitrate ions in solution. But as soon as we hit this threshold of 4.0 times 10 to the minus 5, a precipitate's going to form. And that precipitate is Ag2CO3 as a solid. That's going to be in equilibrium with 2 Ag plus ions plus CO3 2 minus ions. In addition to this equilibrium that's established, we're going to have our nitrate ions in solution plus our ASO4 3 minus ions that are in solution. And now we're going to keep adding silver and keep adding silver and keep adding silver until we reach a concentration up here that's going to be 2.7 times 10 to the minus 7th molar.
Professor?
Yes?
Don't you have it backwards?
Do I have it backwards? Oh, I do have it backwards, sorry. So the these guys right here should be flipped, right? Because 2.7 times 10 to the minus 7 is lower in concentration than 4.0 times 10 to the minus 5. Thank you for pointing that out for me. Okay? So this box right here should be up top here. How about we do this? Why don't I write this figure over again, right over here on this side. But we're going to add it so the concentration is added very, very, very slowly. And this can allow us to selectively precipitate these. So as the silver concentration is getting greater and greater, one of the solids are going to precipitate out first once a certain concentration is reached, in this case 2.7 times 10 to the minus 7. Then when our second concentration is reached, we're going to form both solids. If our goal is to separate them, we don't want to be up in this region right here. And we don't want to be in this region down here. Because in this lower region, we have CO3 2 minus ions in solution plus AsO4 3 minus ions in solution. Okay? So think of this as this little continuum here as you're adding your ions together. One solid goes first, then the next one goes out. And we can calculate these concentrations based on given our KSP values and our initial concentrations of our ions. Okay? Does anybody have any questions about this particular setup and how you would figure out what our best precipitation could be? Yes?
Does that mean that a new equilibrium is established?
So the question here is, well, what happens to the equilibrium that's established, and how is this kind of, this calculation right here is an approximation. Okay? Number one, we would have to account for the volume of each drop of silver. So typically we'll say, hey, this is negligible. And we're going to treat these, and this calculation is a generalization of the two equilibriums happening kind of separate from each other. Because there is going to be a little bit of silver left up here, and you have that battle going on, but we're just going to approximate and do this in this manner. If you want to figure out more of this in depth, I would suggest taking Chemistry 221, and they talk about all of that in there. Okay? So, but for now, we're just going to generalize these and approximate these in this particular fashion right here.